Okay, so I guess I'll start with the introduction. I just want to give a few things, so let's start with that. So yes, welcome everyone to the Fall 2020 Communication and Signal Processing Seminar. I should start by saying I should thank our sponsors. This is basically KLA and the two research groups, NCIS, which is Network Communication Information Systems, and SIP-ML, which is Signal Processing, Signal Image Processing Machine Learning. The other, so this semester, as with everything else, it's all going to be completely online. So thanks for joining in. And to make things somewhat interesting, what you're going to do is add certain new features which you may or may not have seen before. Okay. So what you're going to have is at the end, the speaker will talk for about 45 minutes maybe, with questions. And then we're going to allow, we're going to have one or two discussants, depending on how many people we can get, who then will present something that the speaker will respond to. And this is in addition to other questions. And we also have organized basically a meeting for the speakers remotely with the in a roundtable format, so that the speakers can talk to people. While we cannot replicate an in-person thing, hopefully this gives you some sense of how it gets a little closer to that then. So the speaker for today is Sreeram Kannan. Sreeram is an assistant professor at in the EC department at the University of Washington, Seattle. He was a postdoctoral scholar at the University of California, Berkeley between 2012 and 2014, before which he received his PhD in electrical engineering and master's in mathematics from University of Illinois Urbana-Champaign. I actually met him when he was a student, and we were trying to make our way in Greece from Athens to Volos for a conference. So he's currently an invited speaker at the National Academy of Engineering Frontiers of Engineering US-Japan Meet in 2021, a recipient of the 2019 University of Washington EC Outstanding Teaching Award, 2018 Amazon Catalyst Award, 2017 NSF Career Award, and his dissertation got the 2013 Van Valkenburg Outstanding Dissertation Award at Urbana-Champaign. He's a co-recipient of 2010 Qualcomm Cognitive Radio Contest First Prize, recipient of a Outstanding Internship Award from Qualcomm as well, a few awards at ISC and also an Indian Student Research Contest Prize in 2006. So his research interests are quite broad. His thesis was sort of in information theory, but also looking at, I guess some of the work was published in CS theory conferences. I think he worked a little, that was with Chandra Chakuri as well. He has been interested in the application of information theory and learning to blockchains, computational biology, and wireless networks. So today he's going to talk more about the blockchain part of it, and I cede the floor to Sreeram. Welcome.
Thank you so much, Vijay, for the kind introduction and for inviting me to the seminar. I'm delighted to be here. Indeed, but the first time we met was when I was a student at Urbana-Champaign, and I wanted to write from, I think, Allerton. And I think Vijay was there, and he brought me back from Allerton to Urbana. This is maybe 13 years back. It's a great pleasure to be here to do this talk.
Okay. Just one quick thing before I forget. Sorry, Sreeram, one thing. So yeah, please put all your questions in the chat. I'm monitoring the chat, and then I will periodically stop and sort of collect them and pass them on to Sreeram. Yeah.
Sounds good. Thank you so much. Yeah, please feel free to ask your questions as we go on, especially the clarification questions. We'll answer them right away so that we're on the same page. Okay, so the title of the talk is Blockchains, a Stochastic Systems View. There's a joint work with many collaborators, but a recurrent theme is this joint work with my former postdoctoral advisor, David Shea, and my former PhD advisor, Pramod Vishnath, in most of the projects. Okay, so many of you, when you think of blockchain, maybe you think of Bitcoin, maybe you think of whether there is a price bubble, maybe you think of it's a scam, but I want to start from a somewhat different point here. if you just look around the world, right, digital intermediaries run the modern world. What do I mean by digital intermediaries? This conversation is intermediated by Zoom as a purely digital intermediary. You get on to Uber, is a digital intermediary connecting the rider and the drivers. And if you look at it, just basically the modern world is run by that. And digital intermediaries aggregate information and therefore provide for more efficient market making and also dissemination of information. And they acquire network effects over time and become vested. And what this has done is to lead into a high centralization of power in the AI era. So they have basically power to control and mediate conversations as well as have the data to on which they're building their monetization. So one of my interests or interest in blockchain has been to see if we can remove the intermediary, at least in scenarios where the interactions are purely digital. So a standard paradigm in which one could do it, a classical paradigm in computer science, is the distributed computing paradigm. In the distributed computing paradigm, there are n nodes. They form a distributed computing cluster. Some of the nodes may be malicious, and what can we come to agreement? Can we run a state machine on these different nodes? And so on. These questions were studied beginning with the pioneering work of Leslie Lamport, Nancy Lynch, and many, many others in distributed computing. But what did blockchain really bring? Even though these problems were already addressed in distributed computing, there was one critical assumption. The critical assumption was there is a requirement of somebody to decide who are the n nodes. If you did not decide who the n nodes are that are participating in the distributed computing platform, then if you made it open to anybody to join, then the problem is if you framed your results saying that as long as half of the nodes are honest, then your system is secure. But then I will just spawn up like millions of instances on just my MacBook and take over the network completely. So the paradigm shift that came about when Bitcoin came up was the notion of a permissionless network. There is no permissioning authority who says you are the n people who are authorized to participate. Anybody can participate in the network. So that's a kind of paradigm shift. And because if you have permissioning, then you have an intermediary. When you have a permissionless network, then you have completely gotten rid of a digital intermediary. And the applications extend far beyond currencies, and that's the context in which I want to place them. It's in any context where you want to cooperate digitally, exchange information, do market making, store data, whatever it may be, without having a digital intermediary. So that's the scope of application of blockchain, and that's one of our interests in that domain. Okay, so that's a kind of large scale, high level interest. As people in stochastic systems area, why might we be interested? Randomness plays a very key role in permissionless distributed computing. So, if everybody joins in the network, there is symmetry. All of us are equal, but only some nodes can play certain roles at a given time. So you need some randomness to break the symmetry. So that's one kind of a general purpose theme of randomness showing up. And the second one is, how is this randomness created? This is to make it truly permissionless, you need what I can call as resource-dependent randomness, based on how much compute power you have, based on how much stake you have in the system, how much space you have in your RAM. These are different resources that can potentially mediate how much randomness, how many tosses you get in the system. So, and finally, there's also a notion of verifiable randomness, which we may get to later. Okay, so let's summarize the state of the union, the blockchain union. So where we are, if you just look at Bitcoin, right? One thing that it has really, I think, at this point we can say stood the test of time, is being deployed in the wild for the last 11 years. And really, the core security of Bitcoin has not been broken, which is a remarkable feat, given that it has held values of the order of hundreds of billions of dollars. Okay, but there are other things where and there's also theoretical aspect of security, which I'll come to later. But there are other aspects which doesn't really do well. It's takes as much energy as certain nations. The latency is horrible, several hours to confirm a transaction, and the throughput is not very exciting either. So question is, can we potentially improve several of these dimensions? That's part of the research program. Okay, so before we get into that, let's give a good quick primer, a 4-minute primer on Bitcoin. What happens in Bitcoin? What's a blockchain? So a blockchain is, as you may guess, a chain of blocks. Right? Each block is connected to the previous block through a pointer. A pointer you can just think of as you have put in the hash of the previous block. And so now the question is, how do you mine a new block? You mine a new block, you point to the previous block, put in the hash of the previous block, add in some bunch of transactions, which you may have heard, and then you find the string, a special string called nonce, and this string, you need to find a string such that the hash of all the things together, the hash of the entire block, should be less than a threshold. So you keep trying many, many random strings till one day you got a string such that the hash is less than some threshold. That is called proof of work. Why is it called proof of work? In expectation, it takes a certain amount of time if you try it randomly before you find a string that satisfies this puzzle. So this is called mining. And now your block can be floated and added to the blockchain. Okay. So part of the, like I said, this whole process is a distributed computing or distributed agreement paradigm. So what happens is nodes in a distributed manner create blocks. Each of them are trying to solve the puzzle, and there's a race. And whichever one solved the puzzle first, they float a block. So somebody else solved the puzzle next, they float the next block, and so on. Oops, something happened. Instead of blocks being mined purely sequentially, what happened was almost at the same time. If you observe carefully, it was not exactly the same time, but almost at the same time, these two nodes created a block. So both of them point to the same block. So this is called forking. So they have created two alternate versions of block number 4. So now how would this get resolved? The next time, maybe, a few, so some of the miners, these nodes which solve this puzzle are called miners. So some of the miners will be solving working on the left block, and some of the miners may be working on the right block. And depending on who wins, a block will be floated, right? And now this chain has grown longer. This is now length 5, as this is only length 4. So the prescribed action is everybody follow the longest chain. Okay. So now everybody is just going to follow here rather than here, and the symmetry has been broken at level 4. Okay, so as you can imagine, in a process like this is basically, if you count how many blocks have been mined, what's the length of the chain at a given time, you can imagine it's a point process, a counting process, which is just a Poisson process in this case. And you have this longest chain protocol, which says honest nodes should only mine on the longest chain. Okay, so this is the basic structure of the protocol when there are no adversaries. And over time, what you expect in this kind of a system is that longer and longer prefixes of the blockchain stabilize, right? So if you were at the tip, right, this block at the block number 4 in earlier, block number 4 and 4 prime were not at stable. You don't know which one is going to be in the blockchain at the end of the day. But after 5 and maybe 6 and 7 were mined, maybe you can be sure that this block will remain in the ledger. Okay, so that's the basic idea. And an attack which if you didn't design system carefully is the following. Suppose there's a transaction which says, I buy a car for $10,000 or 10,000 Bitcoin, and then now I got my car, and then what I did is in private I tried to mine a longer chain than what is known in public. Now everybody, after that I release these blocks, then everybody is going to continue mining on the longest chain. And my Honda transaction is now in the dustbins of history, which means the Honda guy got cheated. Right? So this is called a double spend attack. So I issue a transaction which tentatively appears as though it's going to make it into the ledger, and I create a forked version of the blockchain and somehow make it longer. So now if I make it really long, then everybody is going to follow only that chain, and my transaction is now vanished from the ledger. So clearly, a system like this will not be.
Sreeram, There's a
Yeah.
question here. I mean,
Yes,
I
please.
guess this is a standard thing, but so is Poisson an assumption, or is it shown where experiments that the Poisson process thing is relevant?
Yes, so that's a great question. I think when we teach Poisson process in the class, we give examples like buses showing up at the bus stop. I think there are, simple reasoning shows they're not Poisson, but I think this is the closest to Poisson that we can observe in the wild. Because what's happening is everybody's trying to solve a hash. They query with a random hash each time, and what's happening is in a given second, the hash rate is like 1 million or something. So basically it's the correct limit of binomial at the usual NP, and so it's that limit is exactly observed here. So it's practical numbers show that they're of course also Poisson. So it's a very strongly Poisson.
If I can add something to that, there is a basic result in convergence of point processes, which basically says if there are lots of point processes which are very, very rare, then the sort of independent happening, they will converge to be a Poisson process, and which is what is happening in this context. And it's very robust.
Yeah. Thanks, Vijay. That's another interesting way of putting it. Okay, so that's the double spend attack. And the defense against the double spending is don't accept a transaction if a transaction is at the edge of the blockchain. Wait for a transaction to be more deeply embedded. So you take the longest chain, and only if the transaction is embedded K deep, K is like 10 or 20 or 50, only then you confirm a transaction. So now what happens is it's going to be more difficult for somebody to replace that block, because if the public chain is growing at a certain rate and the private chain needs to grow at a faster rate, and essentially you're invoking the tail of the race. So this was already there in the original Bitcoin design, and the Satoshi Nakamoto, whoever that person may be, actually calculated a table showing what is the reversal probability if you accept a transaction if it's embedded KD. And here's the table. And so essentially it's a law of large numbers result showing the security. Okay, so, all right, so that's and here you can see why the security threshold you may expect to be 50%, because if the adversary has more mining power than all the honest guys together, right, then the adversary can grow a chain longer than the public chain easily. But if it is lesser, the adversary's power is lesser than 50% or lesser than the honest power, then there is a parameter K for which you can get safety. So that's the sharp threshold for this particular class of attacks. Okay, so here we only studied this one kind of attack where you try to grow a side chain and then try to make it public. Maybe there are other attacks and the system can be vulnerable. And really, is the system secure? So that's the question. So it is in this context that we formulated this problem of sharp security analysis. The paper is titled "Everything is a Race and Nakamoto Always Wins." I'll explain this title after we get to the result. It's joint work with all these great collaborators. Okay, so Nakamoto only considered the private attack. In the private attack, the white blocks are grown in public, the black blocks are grown in private and released after being mined. And the question is, when can an adversary launch this attack? They can only do it as long if their adversary power is 50%. But there are many other attacks possible. For example, an adversary may try to create a balance between two chains. So both the chains look approximately equal length, and one chain leads for a few instance, the other chain leads for a few instance, and so on. So over a long time scale, you're confused what is the longest chain. So transactions on neither chain can get confirmed safely. So these are called balancing attacks. There are a whole other slew of attacks. So I'm going to just formalize what would be the general adversarial space. Okay, the adversary can decide where to mine a block. The honest nodes only mine a block at the tip of the longest chain. So that's the prescribed protocol. The adversaries can mine a block wherever they want. Second, they can release a block whenever they want. They can release a block, they may mine a block and then hold on, like even in the private attack, they mine these blocks, they didn't release it immediately. They held on to their blocks for some time till it's advantageous for them to show their blocks. Okay, so that's when, so that is control of release timing. Then the adversaries can also control what content to include in the block. We will see, like Shannon's formulation. In our formulation, we are going to be content agnostic. And there is another dimension which is called network timing. Network timing is, we're going to assume that the network provides a broadcast primitive, which means you throw a block into the network, it's going to be disseminated to all the nodes within a certain worst case time called delta. And inside that worst case time, when exactly things arrive for whom, that can be controlled by the adversary. So, and of course, all of these can be state dependent. The adversary can look at the current public state, its own private state, and then decide what to do. So it's a very complicated infinite dimensional adversarial space. And the question is Bitcoin secure against all these dimensions of freedom if you only assume that the adversary controls less than 50% of the mining power? So it is in this context, there is a breakthrough work by Juan Garay et al. It's called the Bitcoin Backbone Protocol. Satoshi in his original paper already argued that Bitcoin is secure against the private attack, which is the double spend attack I showed. But this paper basically considers security against all possible attacks. And it shows that indeed Bitcoin is secure against all of these attacks. It's a remarkable paper. It's beautifully formulated. Underlying it is a stochastics problem, but it's, so the original Bitcoin paper was 9 pages, and this backbone protocol paper is 46 pages, like theory papers are prone to be. And one may wonder whether it is warranted to worry about all these attacks. And it turned out that it is actually necessary, because there are other algorithms which try to improve throughput and other things. They were secure against the private attack, and in fact already promulgated into public systems like Ethereum, but turns out that they have other kinds of attacks like the balance attack. So indeed the security proofs are necessary. Okay, so here we are. So state of affairs, security is proven for 50% adversary only when the network delay is not too high relative to the mining rate. So what is the mining rate? Mining rate is the rate at which, so there's a total Poisson process at rate at which the blockchain is growing. In Bitcoin, it's set at 1 block every 10 minutes on an average. And if the network latency is much smaller than 10 minutes, then security holds. That's what they showed. But what happens when the delta becomes large? That's not known, and that's what we're going to study next. So before we do that, I just want to give a sense. Of course, I can't go into the details of this problem, but I want to give a sense of what this thing looks like. I want to convince you that it's a beautiful stochastic process convergence problem. Okay. And the interesting thing is there is a complex interaction between a stochastic process that is actually happening and an underlying adversarial space of worst case actions. So there is a, it looks somewhat like robust stochastic control, something like that. Okay, so let's understand a simple model. So that's the figure. Okay, so here is the figure. So what's happening is, so you have this blockchain, right? So you have this blockchain, which is 4 blocks, and honest nodes always mine at the tip, right? So there is a, so I'm going to model 2 arrival processes. There's an honest arrival process, which is just adding things at the tip of the blockchain. And there's an adversarial arrival process. When an adversarial block arrives, the adversary can decide to append it to anywhere in the blockchain, right? So that's the adversary's degree of freedom, but the adversary can manipulate where it attaches it, but it cannot fake the arrival. The arrival is when it arrives, because it solved the puzzle or didn't solve the puzzle. That's what the arrival is. Okay, so let's assume for this talk, I'm only going to talk about delta equals 0, which is there is no network asynchrony. When a block is propagated, everybody gets it immediately. So this is the setting. So what's the question that we want to ask here, right? What's the question? So there is a tree process evolving. So a block is a node, right? And each block is labeled either as honest or adversarial. And this tree process is the mother tree, which means it includes all mined blocks, including the ones the adversary has kept secret. So it's just a theoretical tool. And then there's a chain called the longest chain. So this is the longest chain that is kept by the honest nodes. Remember, when delta is 0, all honest nodes have the same view. So they all keep the same longest chain. And the adversary can force the honest nodes to adopt any chain longer than a equal or longer than a previously held chain. So from the mother tree, the adversary can say, hey, now you were holding this chain, now you can hold this other chain. So obviously, even when the adversary does this, the length of the chain only at least doesn't decrease, is non-decreasing monotonically. And so, and whenever an honest arrival comes, it actually strictly increases. So over time, length of C of t actually increases. And the question that we want to ask is, does C of t converge? So this is the fundamental convergence question. So let's kind of like pause for a minute and understand, what do I mean by C of t converges? C of t is the chain held by honest nodes at time t, right? What does it mean by this converges? So convergence of the chain, by convergence of the chain, what we will mean is convergence of all prefixes. Okay, so we'll say that, so given a sequence of chains, we say that the length 1 prefix converges if the first block remains stable after some time. The length 2 prefix converges if the first 2 blocks remain stable after some time. The length m prefix converges if the first m blocks remain stable after some time, right? And C of t converges if and only if for every m, every m integer, positive integer, the m length prefix converges. So this is what we mean by convergence. Any question on this? I think this is the core setup of the problem. Okay, if not, so now the question is.
So Sreeram, one thing, you just want the chain is the longest chain, is it? That's the one you wanted to converge, right? Okay.
That's right. So this is the longest chain kept by the honest nodes. So what can happen is I can have a longest chain. So it's not the longest chain of the tree process. It's the longest chain kept by the honest nodes. So at any time, the honest nodes maintain a current chain, and the adversary can, from the mother tree, because it may have unrevealed blocks, the adversary may choose some other chain which is greater or equal length than the one held by honest nodes and give that and convert. So C of t can be updated by the adversary as I described. Okay. So now it can ask you to switch to another chain as long as the length is equal or greater. And so, and under any adversarial strategy, we want C of t to converge. So this is not purely a stochastic question, because the adversary space has where to mine the block, right? And when to release the block. All of those are controlled by the adversary. So, but the when to release is equivalent to the power of choosing a chain.
Hey, Sreeram, this is late.
Yes, late.
Yeah. So when you say converge, you mean it's converged to like all the blocks, like valid blocks?
No, there's no notion of validity here. Okay, that's a great question. So we don't do any validity. This is what is called a backbone analysis. A backbone analysis. So what are we getting convergence on? So here is what I'm saying. So C of t converges is the same as saying for any m, the first m blocks of C of t converge. So which means there is a time t naught after which the first m blocks of C of t for all t greater than that time remain the same.
Okay. So you could have like adversarial blocks inside this.
You will have adversarial blocks, and that's true. Yes, and that's not preventing convergence. That's correct.
Okay. Okay. Got it. Thanks.
Having adversarial blocks is not an issue because everybody agrees that that's. So once you have a consistent ordering agreed on by everybody, and that is persistent, which means it's going to last over time, then it doesn't really matter whether you have agreed on. So you can separate the blockchain problem into an ordering problem, which is all that we are solving here is an ordering problem. Everybody has ordered the blocks, which means implicitly they've ordered the content inside the blocks correctly, right? Or in the same way, And they've achieved consensus on ordering. Once you achieve consensus on ordering, as long as I have an execution engine, whatever the compiler is, I can run that set of instructions through that compiler and I'll get a state. And all of us have the same state. So that's the key thing. If an adversary includes bad transactions or whatever, those can be easily rejected by the compiler, because the compiler will say either there's no balance remaining or you don't have the right digital signature. So we are offloading all of that and only focusing on the backbone of the process.
Cool, thank you.
Yeah. So that's what we call as the convergence of C of T. Okay. So now the question is, under what conditions can we get convergence on C of T? As you can see, there are only two parameters to this problem, lambda h and lambda a. There's no other parameter right now, right? Since I made delta equals 0. So, and the main theorem is if lambda h greater than lambda a, then C of T converges. Whatever the adversary does, it doesn't matter, C of T converges. That's the structure of the theorem. Okay. So, and more generally, when you have delta, you want to say that as a function of lambda h, lambda a, and delta, when does the chain converge? So that's the main scope of what we want to solve. And I think, before I go into the particular ideas, which may be too detailed at the level of this talk, I want to say that the structure of the proofs goes like this. First, we're going to say that you look at whatever the adversary does, right? If a certain event happens, convergence till a certain prefix is guaranteed. Okay, so whatever the adversary does, if this event happens, that's a purely combinatorial statement that relates all the adversarial space to a certain event. And if this event happens, then you will get convergence till block number n. So that's the first part of the proof, is purely combinatorial. And the second part is that event happens infinitely often or whatever you need to prove. Okay, so this is the structure of the proof. Any questions on the high level structure? Because the disentangling of the adversarial space and the stochastics in our head was an important step in doing this. Okay, so then the question is, what is that event? Is there some nice structure? How do we solve it? And here is the basic idea. The basic idea is you take the blockchain, so you take the mother tree, right? This is not an observable thing that you're doing in the protocol. The protocol is whatever I already described. This is just analysis. So we can assume the existence of this mother tree, which is not observable. And also here I've observed which blocks are honest, right? The white blocks are honest and the colored blocks are from the adversary. And it's not observable, but here we know it. So what are we going to do? We're going to take this block tree and partition it into like this. So we take each honest node and line up all the honest nodes in a line, right? They may not be directly connected with each other, but it's still okay. We just line them up. So therefore the right side system is not a real system. It's a fictitious system. So we convert it into a fictitious system where the honest blocks are in a line, and you put in everything that was mined downstream of an honest block. All the adversarial blocks mined downstream of an honest block, they are built below that honest block. So this block is mined downstream of H1. So these blocks are mined downstream of H2 and so on. So you create these trees. This adversarial tree is now mined downstream of H0. This adversarial tree was mined downstream of H1 and so on. So we decompose the blockchain into these two things. One is a bunch of honest blocks on a straight line. We call it the fictitious honest chain, and these trees which are growing on top of it. And the key idea is we have a notion, again, an unobservable notion called an event which says that if there is a block such that, so if you look at each of these trees, right, each of these trees may be growing over time. T0 will be growing over time, T1 will be growing over time, T2 will be growing over time, and so on. And the maximum rate at which each of them can grow is lambda A, right? Because even if the adversary put all their power independently on each of these, they can only grow at rate lambda A. And what we can do is we can somehow formulate the event that the block 7, the prefix till block 7 is fixed into the blockchain as the event that the fictitious honest chain downstream of H7 is always longer than the fictitious honest chain growing from any of these previous trees. So it's a race between the honest growth and all these different adversarial growths. And it's non-trivial to actually, or it was not obvious how to get this kind of a decomposition that translates, because this fictitious, this is a property of the fictitious system. And what we can show is if this event happens in the fictitious system, then in the original system, block H7, and therefore all its ancestors are fixed, which means you get convergence till block 7. So that's the rough high-level idea. I know I'm not covering all the things needed to do a proof, and that's the main result. The main result is the chain converges if the lambda h greater than lambda a under any possible adversarial action. So this is the idea of, so we call it Nakamoto block, because if this block happens, then the whole thing converges. So as claimed by Nakamoto.
So Sreeram, in a way, does this, I mean, the intuition that you give also sort of tells you the best strategy of the adversary in some ways?
Great question. In fact, that was one of the things we resolved, is actually that for the proof of work model, when the delay is 0, delta is 0, we can calculate the exact worst case strategy for the adversary. But when delta is non-zero, we don't know actually the worst case strategy of the adversary. So we know the worst case strategy of the adversary to the right threshold, which means we just asked, what is the set of lambda h, lambda a under which an adversary can prevent convergence? That we know. So to that extent, we have sharp results. In fact, that's the main reason we called everything is a race, because it's just a race between an honest chain and all these private trees, private chains basically. And so really that's all that is, the race is all that is going on. So you might as well just follow the private attack, and that is enough to put you at the threshold. But the result that we have for delta equals 0 is much stronger. It says not only in the security threshold as you go to infinite number of blocks, but the reversal probability at any finite size is also optimal for the adversary under the private attack. But that's not true for delta not equals 0. So that's an interesting finite block length type question.
So I guess Lei and Ranjan, you guys raised hands. Do you guys
yeah, please, let's go on. This is the main result, so let's talk.
Hey, Sri, so I have a question. So here, assume you fix the length of the prefix block, like it's m, then let t go to infinity, right? And to show it will be converging or stabilized. Is NA finite without saying like how that can scale with?
Oh, excellent. Indeed, we are very sharp. I wouldn't say very sharp, but pretty reasonable exponential rates of convergence. So it does converge exponentially fast, and we have rates.
But okay. So you mean?
So you can show. So here is the type of result we can show. So this event, right? So we showed a certain event. If a certain event happens, then a certain prefix is confirmed. Now you can ask, how frequently does that event happen? Or in other words, you can say, suppose I take a window of length t to t plus L. What is the probability that this event happens inside that window? Because if the event happens in that window, then every block before t gets confirmed. So we can show that the probability that there is no Nakamoto block in a window of length L is exponentially small in L. So that's a finite convergence rate.
See, I have my question is slightly different. So here, for example, here the Nakamoto block is H7, right?
That's
so given 7, like how large the T need to be? So let's say if it's M.
Exactly. So that is related to my question. So to my answer, because now what I'm going to do is I'm going to wait for, so in practice, what are you doing, right? You see the block number 100, right? And the question is, how long should I wait? That's the practical question. How long should I wait to be sure that this block number 7, so I observed block 7. I don't know if it's a Nakamoto block or not. God only knows if something is a Nakamoto block. So I just observed block 7. How long do I need to wait to be sure that I can confirm this block? That's the question. Right. And the answer to that is, if you waited for L time, the probability that the block which is currently inside the longest chain will get displaced is whatever e to the minus something times L.
Okay.
So you see a block and then you wait for L time, and till that L time, if it remains in the longest chain, it will remain forever in the longest chain with probability that the thing that it is.
So that's independent of these 7? Because I thought it will also be a function of these 7.
That's correct. So okay, great question. Actually, the way we analyze it is so now, because you're starting up the system, so there's a finite time effect. So we actually analyze the system running in stationarity. And we have to construct such a system and so on. So that's how we analyze. So it doesn't depend on the block number.
Okay, gotcha. Thank you.
But great question, yeah.
So,
yeah.
Can I ask a question?
Yes, please.
Yeah. Hi. So my question is a bit on the higher, level side. So this, all these things, are you doing it in the main chain, or are you taking it parallelly and doing the security, like so-called analysis?
So here is the thing: we are not changing any protocol or nothing in practice. It's just an analysis of the currently running Bitcoin protocol, just proving strong security results on top of that. So no change in the protocol, no change in how it's going to be executed, nothing. So at this point, no redesign of the blockchain or of anything practical.
So this is your standard like blockchain, the one which like with the longest chain analysis, right?
Exactly.
Okay. And does this process, like, I know this is an analysis, but the fact is that if I had to do this to, ensure certain reliability properties,
yes.
So would it have an effect on the, say, the throughput? The throughput is anyway low. I mean, you just said it like in your beginning slides, right?
Yes.
So would this be like, an additional hammer on the throughput, or like you are just trying to?
That's a great question. So I'll address that. At this point, the security threshold, right? If you look at it, it just says, as long as the honest power is greater than the adversarial power, you're okay, right? So it doesn't really hamper the rate. You can set the mining rate to be whatever you want and everything works. But there should be some cap on the mining rate, because if you just go back to this picture, go back to the, so this picture, so there was forking, right? Just by delay, due to delay, there was forking. And if there is forking, and if you set the mining rate too high, then blocks, next time also there'll be forking, multiple blocks produced within the same time. Next time also there's forking. In fact, the rate of simultaneity is controlled by the network latency. And somehow, therefore, the security can get hampered if you make the rate too large. And however, that didn't come up in that equation. That's because we assume delta equals 0. And you will see the next mean result is actually a sharper analysis for finite delta. Does that answer your question?
Yeah, it's okay. I mean, I guess I was just trying to see, like, given that the original protocols anyway had a low throughput, but if you're trying to do this, which is pretty cool, by the way, but probably might add more overhead on throughput. Yeah.
It is going to make everything, I mean, so the thing is, right, like the existing protocol is by itself, right? There is this table, for example, is not accurate. The table that Nakamoto calculated. Right? So if you wanted 99.99% reliability and you set that, but it turns out there's a different attack wherein actually your reliability is 93% or maybe only 60%. Right? That could happen in Bitcoin because he analyzed only one attack. What we're doing is giving an ensemble analysis saying that whatever attack the thing does. So the only way it translates to anything in practice is the setting of the confirmation parameter. How deep should you be embedded to be sure?
Okay.
And that, of course, affects latency. And I'll mention a bit about our ideas on how to solve these problems. But at the moment, I'm just presenting a purely armchair theory result on.
Okay. No. Yeah. Thank you.
Okay. So here is a cool result, which is, like I said, actually, this result by itself is not new. This result, even though our way we formulate it and, the continuous time, there are certain aspects which are new, but really the core structure of this result is already there in the Bitcoin backbone protocol. But what is not there is what happens when the delta is not zero. The network delay is not zero. And so now the question is, for a certain lambda is basically the total power, lambda A plus lambda H. And lambda delta is the thing that matters. Lambda is blocks per second and delta is seconds per block, right? So it is the right unit. And if existing security results, for example, let's take the red one. So these are all like cryptography papers trying to analyze the thresholds. And what you can see is they all give you some guarantee. They say that if you're below the red line, for example, this is the adversary fraction, which is lambda H, lambda A by lambda A plus lambda H. The adversary fraction is less than 0.3 and this ratio is 1, then you're secure. But if it's 0.4, you don't know if you're secure. Whereas our theorem shows that you are secure. And if you go beyond it, if you go beyond the blue curve, then you're not secure. So it's a sharp threshold result for convergence. Is this clear at high level what I'm trying to say? So you have a finite delta and you can ask for a given lambda, which is a given mining rate, till what adversary fraction are you secure? And existing papers have different levels of results. And we have the first sharp characterization of the security threshold. Okay, so now let's go back to the table.
So Sreeram, the lambda there is
lambda A plus lambda H, the total rate of mining.
Okay. And and you're saying this is basically so 1 over that. So this is in the regime where you could have forking in some way.
Yes. So if lambda delta is large, then you have a lot of forking. And even when you have, so the question was when you have a lot of forking, then what's the security threshold? And I would say it was not known. In fact, it was conjectured that there may be attacks. The threshold is not, it was easy to calculate the private attack threshold because it's just a simple attack, but is really a converse result showing that there's no other attack which can be worse.
All right, thank you.
Yeah. Okay. So that's the picture. So I don't think I have time to go into any of the other results, but let me just state the structure of these other things. Okay, let me use 1 minute to say what the energy efficiency is. The energy is wasted because you're using proof of work. There is another thing called proof of stake, where you get to propose a block depending on how many coins that you already have in the system. So it's called proof of stake, and we have a new proof of stake protocol. And since the stochastic systems audience, I'm just going to highlight the interesting models. So earlier in the proof of work model, we said that when you mine a block, you're going to attach a block at any one of the places. It turns out in the proof of stake, or at least one version of proof of stake, what happens is you can attach a block at many, many places simultaneously. Okay, so you take a block and then you can attach it. Whenever the adversarial mining event happens, the honest nodes are honest, so they're going to follow protocol. They'll only attach a block at the tip of the blockchain. But an adversary can attach the block at many, many different places. And what that does is, if you just count in a volume sense, how many blocks that the adversary makes and how many blocks that the honest node makes, the adversary makes way more blocks than on what honest nodes can make. So standard analysis, existing analysis breaks down under this setting because they were using volume arguments. But if you see, the longest chain of all of the adversarial things got extended only by 1. So the rate at which each of the trees are getting incremented is not much. And so we extended our results to solve the proof of stake problem as well, which is this thing, and again get sharp thresholds. So I'll not cover this. There is another dimension which is called proof of space and some other proof of stake protocols, where what can happen is a third model. So here is the third model. This is again another interesting stochastic model where if you have this underlying blocks, so in the second model that we just saw, what happened was when a block was mined, it can be attached to all these different, any existing block or any or all of them, right? That's what the adversarial mining is. But in this proof of space, which is a different resource control model, what happens is the block, when you mine it, you can, so the way you think of it is each block in the blockchain gives rise to an IID new point process for the adversary. Okay, so here there was only one arrival process and you could attach the block anywhere or many places. Here you could attach in one place, here you can attach in many places. Here what's happening is a new adversarial point process is spawned whenever a new block is produced. So this is an even more complicated model. And really our main understanding in the Everything is Erased paper was this one. So in this model, things were understood in delta equals 0. Here also it was understood in using different proofs for delta equals 0. And here nothing was known in terms of security. And we have a single kind of methodology that solves all these problems and finds exact thresholds for all of them. The third one has its own like beautiful set of structure. For example, to analyze this, you have to understand these branching random walks and calculate the rates of growth of certain branching random walks. And we have some nice results there, not only in just analyzing this existing proof of space protocol, but also in figuring out how to improve. So the existing proof of space protocol turns out to be safe till a threshold of 1/1 plus E, which is 27% instead of 50%. And we proposed variants using this branching random walk theory that can actually achieve security till 50%. So that's the, so that's the story there in terms of energy efficiency. So you're getting basically all the properties like Bitcoin, but without any energy wastage. We have like a bunch of different projects trying to solve latency and throughput, but I think in the interest of time, I'll stop here. I'll just highlight one thing which may be useful in general, a way of viewing the blockchain. Okay, so one way to view the blockchain, right? Like we have the ISO OSI 7-layer architecture for networks. We have an understanding of what layers are in a wireless stack. So what's going on in a blockchain? So you have an underlying peer-to-peer network, and the peer-to-peer network needs to maintain, make sure that each node only maintains local state and somehow give rise to a broadcast perimeter, which means if I want to do broadcast, then it should reach everybody, or depending on other types of blockchains, you may require also multicast delivery through the peer-to-peer network. So the peer-to-peer network needs to be designed for these features. How do you design these efficiently is an interesting problem. We have an algorithm here called Perigi, which tries to efficiently adapt neighborhood structures of peer-to-peer network to solve this problem. And there's some very interesting exploration-exploitation trade-off on multi-banded stuff that shows up here. Okay, the next layer is consensus. Consensus layer assumes that there is a broadcast perimeter. You throw some block in, and then that's going to be broadcast to everybody. And so again, the goals of the consensus layer will be things like, is it secure? What's the throughput, latency, fairness, maybe incentives. So you have all of those in the consensus layer. The core results I presented today fall under a consensus. Then one layer top of it is something you can call as sharding. Sharding is how to distribute the resources across multiple nodes. And again, very interesting ideas from coding theory, from robust resource allocation and dynamic game theory show up here. And finally, you can build applications on top. For example, Bitcoin as an application or other decentralized finance. Many different applications can be built on top, and all of them require, again, incentives and mechanism design to go with it. So I just use this as an invitation for all of you to participate in this project of bringing ideas from information theory, networking, control, game theory to solve important problems in blockchain. With that, I'll stop. Thank you so much.
Sreeram, thanks. So now we're going to go to the discussion part. And so I think we can start with Norman. So if you want to share your screen and then present that, then so you will present for about 5 minutes, and then Sreeram would respond. Then we'll have the second one, second person start. Right?
All right, sure. May I ask if you can see the screen?
Yeah, you can. Why don't you just make it?
Yeah, firstly, thank you very much for such a wonderful talk. This is certainly an interesting work that has piqued my interest once again. I do not have much contributive substance to say here, so I will just take this time to summarize the talk of Professor Sreeram. So just quickly going over what we discussed, Satoshi Nakamoto basically claimed the security of his original proof of work based longest chain protocol by analyzing the private spend attack. And the main question of this work was to determine if the private spend attack was indeed the worst type of attack. And the answer to that question in light of this work is yes, for 3 different classes of protocols, which Sreeram also went through: the proof of work model, the proof of stake model, and proof of space model. And as we saw, the proof of space model gave much more adversarial power to the adversary. And one thing that I would like to mention, and something that is very good in this work, is that it has successfully segregated the cryptographic aspects from the stochastic elements that are involved in the blockchain. To study these classes of protocols, it basically does 2 important things that we also saw. And those 2 were the notions of the Blocktree partitioning and Nakamoto blocks. I will not go over through this this figure because this was discussed before. I think one important thing to mention here is the effect of delta, because I think what we discussed previously was the case when delta was equal to 0. If we introduce a non-zero network delay, there are 2 important things that happen in this concept of Blocktree partitioning and Nakamoto blocks. And the first thing is that you will have more forking, because the adversary has now the power to create a difference of opinion amongst the honest nodes in terms of which chain is the longest chain in the network. And on top of that, even if you have a certain honest block and there's a tree that follows it, the number of arrivals of honest blocks that come after it, they get sabotaged by the forking as well. So it's like a cascade effect that is involved here, which requires some more analysis. This is one key figure from the paper in which it has been shown, it's the numerical evaluation, that the true threshold is actually indeed the private attack threshold. And if we look at figure C, for example, you can see that we see the numeric value 1 over 1 plus E. And this is because in the Chia's proof of space adversarial model, the adversary has much more power in terms of the lotteries that were given to each honest block. So that's about it from my side, I guess. Yeah, thank you.
Thanks, Norman.
Yeah,
Sreeram, do you have any thing to add or comment or anything, response of any kind? Or
no, I guess, it was a good summary, especially the delta greater than 0 case, which we did not cover.
All right, thanks, Norman. I think now I'm going to cede the floor to Dengwang, who's our second discussant.
Sure.
thank you.
Okay, let me share.
Stop sharing the screen, Norman. Yeah.
Yeah, I can stop.
No. Yeah, you can share. No, Norman had to stop sharing screen.
Yeah, I can stop him sharing this screen.
Okay.
I can override, I mean. So, yeah, so basically, first, thanks, Professor Kannan, for the presentation. So here, what I have been assigned to is another excellent work of his, which I don't think is covered in this talk. So I will address a little bit of what this work is about. So just the first thing is just to quickly remind anyone who are not familiar with the blockchain is a growing list of blocks, as already mentioned, and it requires some sort of security. And the most important feature is that it is a distributed system. So there's no centralized entity storing the data and everyone asking the centralized entity. It's distributed. Everyone have a copy of the entire list, and they somehow do transactions based on consensus. So, however, this can cause computation and storage efficiency problems when the chain goes larger and larger. So the sharding protocols come into play to solve this problem. Basically, the sharding protocol, in plain words, is to dividing the list of blocks into pieces and allow each node to store only a piece of the entire data rather than the entire data. However, this can create security challenge. So there is a trade-off between security and computational efficiency. So according to this paper, there's at least 3 key features needed for a blockchain to operate. First is scalability, computation and storage efficiency. Second is safety, which is the existing record cannot be easily, at least, altered. This was also mentioned in the talk that after a certain time, some transactions stay there forever. This is desirable. And the third one is liveliness. Even if the adversary cannot hurt safety, sometimes the adversary can cause liveliness problem, which is the adversary just blocks new transactions from coming in. So if you, for example, if you require the chain to do a lot of safety work, then the adversary can use that to block new transactions from happening. This so this also should be guaranteed, and existing protocols cannot ensure all of them at the same time. For oftentimes, the scheme can only guarantee 2 of them while sacrificing the other. For example, the multi-consensus architecture sacrifices safety. The uni-consensus architecture sacrifices liveness, and there are many others which are not very scalable, but satisfy the above, but they are not very scalable in general. So in this paper, the authors propose free-to-shard architecture, which ensures all the aspects above. Basically, what they do is they design an architecture based on the uni-consensus architecture, which I mentioned here, doesn't ensure liveliness, but ensure scalability and safety. And they basically design a dynamic self-allocation scheme to ensure liveliness. So the key contribution is this dynamic self-allocation scheme. At the core of it, it utilizes Blackwell's approachability theory. And if I want to briefly explain what is at the core of it, this is what is at the core of it. It's a dynamic game. So you have n nodes, you can think of them as boards, and k shards, you can think of them as bins. And some proportion of the boards are honest, some proportion of the boards are adversarial, and honest board, at each time, honest board assign themselves to the bins, and adversarial boards observe the actions of the honest boards and then decide how to assign themselves to the bins. And the honest nodes want to maximize the minimum, the worst case, the worst shard, the performance of the worst shards given the adversarial strategy. And this this performance metrics is based on a time average of
the proportion of good nodes in each bin. So this is a simple dynamic game which is at the core of this work, and the authors beautifully applied Blackwell theory to provide the answer. And the authors first show that it is impossible to make R star greater than beta. Then they provide some strategies to approach beta. And this strategy is offline, which means that it's a sort of experiment. You have a centralized planner to assign honest nodes to shards, but somehow the nodes need to do it themselves. So then, by modifying this scheme, using the idea of this scheme, they arrive at a dynamic self-allocation scheme, which achieved the same performance. So the strengths of this paper, in my opinion, are follows. First is weak assumptions on adversaries. So it's a very weak assumption. Adversaries can do whatever they want after observing what's the entire system state, basically. And the safety is guaranteed as long as the total proportion of adversary is below a threshold. This is also desirable because this is weakest assumption possible. If the proportion is large, you cannot do anything about the system, which is also the same as is in the talk. And it's very flexible because it doesn't require a centralized mechanism to allocate nodes to shards, and it only requires a certain proportion of nodes to follow the allocation policy for Leibniz guarantee. And the proposed algorithm matches what is theoretically the best. And this core algorithm, in my opinion, are also of independent interest in, for example, queuing systems, and probably many others. Here are some potential weaknesses that I think there could be. First is, how do we have a good idea on the proportion of good nodes at last time step? Because the algorithm needs to use that information to compute the allocation at the next time. But how do we reliably estimate this information, even we don't directly know that? Can adversaries corrupt this part of the data to mislead the honest nodes to believe that they're a smaller proportion or larger proportion? Or they can pretend at time t just to mislead at t+1. Can these things happen? And as I have mentioned in a talk with Professor Kannan, is time average a good metric? What about the time average of expected delay? That will be a different metric, and that will require a different solution. Some potential future work, one of them is to incorporate load balancing scheme in self-allocation. So basically in this work, after you arrive at a target distribution of the nodes, then you want the nodes to allocate themselves to get close to that target distribution. As we have known in the boards and bins literature, suppose you have a target distribution that is uniform, and then you have a lot of boards which uniformly choose a random bin, then what you get is most likely look like a boson rather than uniform. So you will need some load balancing kind of technique probably to do it better. In this work, they show that this is not necessary, but maybe utilizing some load balancing technique could be beneficial in practice and also in proving all these results. And another thing is, can we have multiple shards per node? Not a lot of shards, but constant, for example, maybe 2 shards per node can make a difference comparing to 1. I don't know the exact answer, but maybe that makes a difference. What does that give you? Does that give you any advantage? And other performance metrics, which I have already mentioned. So yeah, these are here. I'm over time. I apologize for that.
Oh, thanks, Dengwan. So Sreeram, would you have any comments or anything?
Yeah, thanks so much, Dengwan, for covering this. It's good that I didn't talk about it. It's a very good summary of what in 5 minutes that you can give. Can you go to the previous slide? I'll address some of the weaknesses and also maybe list some open questions here. This one, the first one, actually, we don't need any idea of the proportion of honest nodes. This is something that notes we did not make it clear, but I think the protocol itself needs only to estimate the total number of nodes in a given bin. It does not need an estimate of the number of good nodes, and that's an interesting thing. And you can recursively estimate that. It's there somewhere, written somewhere in the paper, but it's a so this part actually, many of the reviewers were completely confused by this exact point, and turns out you don't need that, and it's so that's the answer to the first one. The second one actually is a very good point. Actually, what we've done is the time average thing that we are calculating, the R of t, is basically the average throughput, right? So it's a coarse metric. Mm-hmm. The average throughput per shard. So you have these K applications. Think of K applications as K shards or K bins, and we're calculating the time average throughput on each of them, and we're optimizing for that. And the results show that you can. The really shocking result with this is that even if the adversary allocated itself statically, you cannot do anything better than that ratio, and you can get the same thing even if the adversary allocates statically, even as long as you're also responding, even if the adversary allocates adaptively, as long as the honest nodes are also responding to it. But that was only to the level of throughput. So what is the level? So if you go one level finer, you have latency. And I think that's where both this point, and the next point. Can you go to the next slide?
Yeah, just coming up, I thought maybe there could be some quality of service method.
Exactly. And even inside this, right? So there are very nice, I think, theorems to be written in. So if you go back, I will just point out some to the one with the equation. Yes. RK of
That's why it's equal.
Yeah. So here we're taking the long-term time average, right? And one question would be, can you guarantee anything about short-term averages? So here what it guarantees is that the long-term time averages converge. But what is the shortest horizon at which you can guarantee that the short-term averages will also converge, so that in any short amount of time you have, so that problem relates to all of the other stuff you talked about, including load balancing and latency. And so that's an interesting open problem. I don't think we could get very good.
In your paper, you have you prove this, and you have
basically convergence. Yeah.
Square root of t result.
Yeah. But that's exactly. So I think it depends on n. I think in some way, but that's not. I think that can be improved. That's what I'm saying. And that may also have a bearing on both the this point and the next slide. The incorporating load balancing, right? So we did not have required the load balancing thing you are talking about, because again, we were only talking about throughput, and to the extent of throughput, uniform sortation is good. You don't need any fancy algorithms. But when you talk about latency, they'll become important. And multiple shards per node, we did not talk about in the paper, but it's it is automatically adaptive to that. A node can belong in multiple shards and stuff, and the algorithms do. Okay, thank you so much for the great summary. And
thank you for the talk.
Yeah, thanks, Sreeram. Any other questions anyone had? If not, let's thank Sreeram, sir. Yeah. And then you're meeting with a few people tomorrow. To thank you again for giving all the time to meet with people, and I hope it's helpful for both sides. Well, I think there's a raised hand. Ranjan had a.
Yeah, I can. I'm here to talk more. Hi, Ranjan. Please go on.
Oh, maybe he's muted. Let me see if I can unmute him.
Hello, can you hear me now?
Yeah.
Yeah. So I had a question about Dengbang's slide. So when he talks about this Blackwell approachability, so are you implying like convergence to mixed equilibrium, like the Martin convergence theorem? Is that result? When you say approachability?
So no. So this is basically the result is the following. So if you have a vector valued game, right?
Okay.
Like, so you have a game not with a scalar objective, but a vector objective.
Okay.
Then Blackwell characterized what possible values of the reward set, right? So now the reward is a vector.
Okay.
So now what possible values of the reward set are achievable no matter what the adversary does.
Okay.
And came up with a dynamic protocol. Basically, you look at the set, and then wherever your current average reward is, you just jump on the other side of the hyperplane and then stuff. So there's a beautiful result.
But
And
it's a
that
mixed
result
equilibrium.
has,
Is it
sorry?
a mixed equilibrium? So when you converge to
So
an equilibrium,
okay. The Blackwell approachability can be used to achieve correlated equilibrium. I don't know if that's what.
yeah, because I was just trying to think, like, when you achieve the equilibrium with respect to like the strategy set, so is it like a fixed, like, pure strategy, or is it like you have certain strategies which are like, you randomly have distributions over that?
Yeah, so that's a good question. So there are actually two levels of description of the problem, and I think Deng Wang mentioned it briefly. One level is when it's a two-player game. There's all the honest players are coordinated, all the adversaries are coordinated. But in practice, there is another level where the honest players are not coordinated. The honest players are distributed, but the adversary is coordinated. So that's a two different types of game. In the first one, where the honest players are fully coordinated, there is no, in the way that we have our problem, you don't need to do mixed strategy.
Okay.
Because what the strategy is a kind of fluid allocation of resources across the K bins, right? So you have K bins or K shards. You're kind of saying you allocate 99.93%. So we allow that. It's a kind of theoretical game. So we allow that. But if you want to approach it in practice, then you would say that that's the next part where we say that instead of it allocating 99.993 of all your resources. So we don't pay attention in the first setup to the finiteness of n. But when n is finite, then you have to use randomized strategies, which are randomized according to the proportions that you see. And then we also show that you get the same convergence.
Okay, thank you so much. I just had one quick question on when Deng Wang
Actually,
said.
Ranjan, can you take this? You're meeting him tomorrow, right? Do you want to take
Okay,
the
no
question
problem.
after? Let's stop now
sure.
because everyone's on. Yeah.
Okay, thank you. Yeah.
Thanks. Yeah. Thanks
so
again,
much,
Sreeram.
and everybody.
Yeah. Sure.
Right. Thanks, Sreeram. Yeah.
Yeah, thank you. Thanks so much for the.
Bye.